all of these questions. They're just proofs, and you're going to need to try and think of some way to do them. Figure it out yourself. But they do come in two main groups. So you can prove them by using a little bit of algebra, or you can prove them by using a diagram. So what I'll do is I'll do one of each and then let you try some of them to give you the idea. So for example, I'll do as an example this colour's a bit messed up, I know. Is it blurry? Cara, try and fix the lens a bit. Oh, no, worse. Other way. Yeah. Yeah. What? No, that's really it. Yeah. Okay. So I'll do as an example question 1, and then I'll do which one do I like? I like the circle one. Yeah, I'll do, actually that's funny, I'll do 1 and 12. So number 1, here you go. In number 1 you want to prove, yeah. In number 1 you want to prove that x1, or just x, is it? What letter do I use?
Just x, sorry.
X dot x equals magnitude of x squared. So the way we can prove something like this is by saying let x, just call it something like alpha, beta, gamma, doesn't matter. Doesn't matter, whatever. ABC, whatever. So if you start at the left, you get x dot x equals alpha, beta, gamma dot alpha, beta, gamma, which equals alpha squared plus beta squared plus gamma squared. Yeah? On the right, magnitude of x squared is squared square root alpha squared plus beta squared plus gamma squared, which is equal to alpha squared plus beta squared plus gamma squared. It's the same. So therefore, x dot x vector is the same as the magnitude of vector x squared. And that's the end of the proof. So this is one way you can do a proof, or one type of proof you can get. Yeah, so write that one down as an example. Wakey, wakey. Yeah? Can I scroll down?
Yeah.
I can scroll down?
Yes.
Yes? Okay. So, number 2. I want you to, well, I don't know if this is necessarily number 2. It's just my example. It might be in the book already as a question. So I want you to try and do something similar to prove that vector, well, we'll use or instead of x. Vector or1 dot vector or2 plus vector or3. Did the colour just come in?
Yeah.
For some reason. Equals or1 dot or2 plus or1 dot or3 3. Too much light.
R1.
Now the colour will probably go now, so I need to move it. Oh no, it's alright.
So the
Can you see what's happening?
R1.
R1 dot R2 plus R3 is the same as R1 dot R2 plus R1 dot R3. Okay? Now I'll just give you a minute to try that. So first, did you write it down?
Can you take a number? Can you choose R1 as a number?
What do you mean?
The R1 is equal to 1.
No. Definitely not how we prove stuff in maths.
Choose the letter.
You can choose a letter.
Yeah.
Finished already?
What?
Give Slowpoke a few more minutes.
Oh, it's very easy. It's very good.
Show me what to do. Right. No.
Oh.
What do you mean?
This is the proof?
This is, yeah.
Yeah, no.
Oh.
He just did a simple algebra thing. Opening the brackets.
You don't know that the dot multiplies like this. You don't know that you can expand like that.
You can.
No, but you don't. No, but I never told you that this is a rule for vectors.
Yeah.
KJ, will you?
Stop your sarcasm.
No, Fahad, you don't know that the dot product can multiply brackets like this. You know what I mean? Like the dot product might not be the same as multiply. For example, we know that x dot y is the same as y dot x
Yeah.
because we proved that. But for example, I'm trying to think of something where it's not true. Oh yeah, I'll give you a good example, okay? So for example, if I said x dot y equals x dot z, we cannot say y equals z. They don't cancel. And you can see this with actual numbers. Like you could pick x as like 1, 1, 1, and y is 0, 1, 0, and x is 1, 1, 1. I might have to pick different numbers. X is 1, 1, 1, and we'll say y. No, we'll say that y is 1, 0, 0, and then x here is 1, 1, 1, and z is 0, 1, 0. So what's this when you dot them together? What do you get?
1,
1.
0, 1.
1.
Yeah.
And when you dot these together?
1.
1. But if I cancel these, is this true?
No.
No. So you don't know that vectors could multiply like that. That's my point.
The slowpoke is finally done. And you cannot tell me no for this.
Okay.
Yes.
Right, let's try and fix these equation of the line answers. Number 2.
This is your book?
Yeah. I'll have to work the answers out.
Which one?
From page 78.
Are we waiting for the other slowpoke?
We are.
Good luck with that.
Wait a second, Fahad. Question 2. Wait a second. Wait, cotton picking second here. Number 2, I said in each case, the first vector points to some point on the line, so that's A,
Yeah.
and the second vector points along the line.
Parallel.
No, that's AB.
Yeah.
That is AB, not B. This is AB. It's parallel. This is AB. Look at your question. Where is it? Here? This is it? Hey James, I didn't do any of these. Go over there now and I'll give you a piece of my mind. AB, you didn't need to calculate. I gave it to you.
You already able.
Yep.
I know I have discussed that.
Each case the vector points to a point on some line, and the second vector points along. Okay, so this is parallel, but
So this means maybe why
this is not parallel. Like the lines are parallel.
No, I'm saying the second vector is AB. It's on the line.
Along the direction of the along the direction.
So it's on the line. Or along, it doesn't matter. Vectors that are parallel are the same.
Yeah,
But what? They're the same vector.
yeah.
Completely the same. Yeah. So you have vector A which points to the line,
Yeah.
and you have another vector which is parallel to it. That parallel one is AB. Do you remember I did 2 examples? This is like the second example. Alright, did you prove this? Here. Get off the phone. Right, so let's try and prove this.
Even on that you calculated BC.
Well, maybe it's wrong still.
You try this again.
But yes, we know you are wrong.
No. It looks right to me, Fahad. So if I do, this is A,
Yeah.
and this is AB, so if I do this plus T times this, 1 minus 1, 3, 1 minus 1, 3, minus 9, minus 2, minus 8, minus 9, minus 2, minus 8, looks right. You can check it in a minute, but it looks right to me. What?
Or can you explain after this?
Have you got the examples from the class?
Yeah.
So,
Oh,
it's like this one, except I give you BC already. No, I gave you A and BC.
Yeah.
Do you know what I mean? This here is A. I gave you. This here is BC. I gave you BC.
Okay, when you say it's like A in that first term, for example, these are 2 points, there is no C, okay? So if you want to make an, you need to
No, but I gave you BC.
you said along.
Yeah. Is BC along the
But
line?
it is parallel, it's not on the line. So you have to.
Ah! I told I told you before, if 2 vectors are parallel, they're the
Yeah.
same.
Yeah,
Yeah.
parallel.
Yeah. So what's wrong?
Then only the gradient would be same.
No, they're exactly the same. Parallel vectors are identical. If I call this vector A, and I call this vector B, that's the same vector. They're completely 100,000,000% the same. There's no difference. 0 difference. So, in that question, what I did was, I gave you A, like this, and here's the line. This is what you're picturing, yes? And I gave you a vector which points along the line. Now, it doesn't have to be on the line. It could be parallel to it. It doesn't matter.
I know.
Yeah. So, you have here, like, if I draw it here, I can also draw it here. So it's A plus T times this one.
If you said,
Yes.
if this formula is like y is equal to mx plus c.
Yeah. And the important word there, like.
Yeah.
I didn't say
so,
it, yeah.
So this would be like a gradient.
Like a gradient, yes. Yes.
So if the like two equations are parallel,
Yeah.
so AB would be same.
Yes.
Same, right?
Mhm.
So how do you think this is AB? So
How-
making the question.
How do I
You
think
gave
what?
like two different points.
I gave you two different vectors, yeah. So A, which is like this vector, yes.
Yeah.
And then I gave you another vector, what will we call it? What will make you happy? B, BC? Here it is here. Whatever.
Okay.
B. Yeah? So I said A is on the line. So here's the line.
It said in each case
Yeah.
the first vector points to a point on some line.
Okay, so we agree with this.
Yeah.
Right, so I'll tick this. Yeah?
On the and the second vector points along the direction of the line.
Yeah? So look at my picture. Does B point along the direction of the line?
Yeah.
Okay, so wait. So tick.
Yeah.
Okay. Right.
Find the equation of the vertical line in each case.
Yes. Yes.
Yeah.
So this is find the equation of this line. Yeah.
It's not vertical, it's the blue one is vertical. Okay, just say okay, it's the same.
Huh?
That's not
No, not vertical. Vectoral.
Oh yeah, that's not.
Yeah, but it doesn't matter. I know what you mean. Yeah. So we can draw the B here, can't we?
Yeah.
Yeah. So if this is A and this is B, then it would be A plus TB.
Yeah.
This will be the vector that's on the line, that points to the line.
Okay.
So the downside.
I think I very smart.
In direction of the line, meaning.
Because I saw every picture.
Good for you. And they're all right?
Yeah.
I think that calls for a celebration sip of coffee. Tastes better. It's difficult. There's difficult concepts here for sure. For sure. You might want to watch the video again.
I tried, okay. You didn't even try.
Yeah, that's right.
That's right. No, I don't work my assignments on this book. I don't work my assignments on this book.
Yeah, sure. They're in your book at home,
Yeah,
are they?
exactly.
Oh, yeah. All right, let's look at this one now. Right, so we'll call R1 X1, Y1, Z1, and then R2 X2, Y2, Z2, and then R3 X3, Y3, Z3. What's wrong? What could possibly be wrong?
Ooh, because I did R1 XYZ,
Yeah.
R2 STU.
Fine.
R3.
That's
good.
That's fine.
Okay.
Right, so on the left we have R1, which I know. What's R1? X1, Y1, Z1. And then R2 plus R3, that would be X2 plus X3, Y2 plus Y3, and Z2 plus Z3. And then here, X1, Y1, Z1, dot X2, Y2, Z2, plus, you get the idea, X1, Y1, Z1, X2, Y2, no, 3, X3, Y3, Z3. So if I look at the left, that will equal X1 times X2 plus X3 plus etc. And then if I look at the right, I'll get X1 times X2 plus Y1 plus Y2 plus Z1 times Z2 plus etc. Now when I write etc, I'm just being lazy. By etc I mean the same thing again but with the Y, and the same thing again but with the Z. Same thing again with the y, same thing again with the z, plus x1, x3, plus etc. Now, are these two the same?
Yep.
Yeah, because here you have x1, x2 plus x1, x3, and here you have x1, x2 and x1, x3. So, that ends the proof for that one. Yeah? Right, so now this is the proofs that involve using some algebra, but there are proofs now that involve using some diagrams. Okay, can I go down? Yeah. I'll show you. So for example, here is a semicircle, and it doesn't matter, radius is or, whatever. So here, the radius is or. And you might remember this one from high school, but if you draw a line from this point on the diameter to any point on the semicircle circumference, and then back down to this point here, this here must be 90.
Yeah.
So we want to prove that using vectors.
Is this over here?
This is, I think, the last question, number 12. Is it?
Yeah.
Yeah. Right, we need to give the points some name.
ABC.
Yeah, we could just do it.
K.
ABC.
K.
Yeah, it doesn't matter.
K.
Right, I'll call this one the position O, the origin. We can call this one A, we can call this one B, we call this one OR. So you want to prove what as vectors? As a vector statement, what are you trying to prove?
The angle A.
Yeah, but as vectors.
AR is perpendicular.
That is right.
RB.
You want to show that AR is perpendicular to RB. Or BR, yeah. Which means you want to show that AR dot RB should equal 0. Yes. Wiki. AR is R minus A, and RB is B minus R. So we can multiply these out because it was one of the proofs earlier which we did a little bit of, that vectors expand like regular multiplication. So we get R dot B minus R dot R minus A dot B plus, pen's gone, plus A dot R. We want to show that equals 0. Now, if you look here, I can probably do some cancelling and cleaning up. We got A. Yeah, now actually what we can do, maybe I should have done on the previous line, but if you look here you can see that OA, or A, is the same as BO, and BO is the same as minus OB, which is the same as minus B. So in fact, it's no surprise that A is the same as minus B, because they're the same vector, but they're just pointing in opposite directions. So we can change the A or the B, it doesn't matter which, so we'll just change the B's into minus A's. So here we get minus R dot A, minus R dot R, plus A dot A, plus A dot R equals 0, by using the result here, A equals minus B. Now, two things cancel here. What cancels? No, the A dot R is the same as minus R dot A, so this cancels this, yes?
Cancel how?
You can add.
You add them because you're going to flip the sign.
Yeah.
You're asking me something or what?
Yeah. No,
Why
like,
do you cancel?
why we can?
That's AR.
Yeah.
Yes.
Oh.
Mm.
Wait, no. This is the same as this.
Yeah, but they should add up, not cancel.
Yeah.
No, why don't they?
Yeah, it's just that.
Minus or dot A is the same as minus A dot or.
So, don't cancel.
No.
No.
Yes?
No.
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 This is something we proved in the last class.
Yes. Yes, okay. Okay.
Do you remember?
Yes.
That for dot product you can swap them and the answer's still the same. You're thinking of this. You're thinking of AB and BA, aren't you? No, this is or dot A and A dot or.
Okay, yes.
So here on the next line, if you want to make it clear, this is minus A dot or. Minus or dot or plus A dot A plus A dot or equals 0. Now this definitely cancels this. So they're gone. So you have A dot A equals or dot or. Now what is A dot A? We did something today about that.
Magnitude of A squared.
The magnitude of A squared. And or dot or? Magnitude of or squared. If I square root both sides, what do I get? Magnitude of A equals magnitude of or. Now is this true or false? Is the magnitude of A the same as the magnitude of or? Is the length of the vector A the same as the length of the vector or? Yes, because it's a circle. So you know that this is true, which means the previous was true and the previous was true, etc. So this goes all the way back, so we've ended up proving that this is true.
So now how do you make sure it's like they're perpendicular?
We know that, what? What are you asking me?
The last step was the magnitude of A equals the magnitude of R.
So this statement is true, isn't it?
Okay.
So it means all previous statements were true.
Okay, there you go.
Well, really it means the first statement was true. If I ended up with something false here, it meant that the first statement was false. But you can imagine this proof running backwards in your head. So, look here, is it true to say the magnitude of A equals the magnitude of or? Is that a true statement? No, this isn't a trick. It's true, isn't it? Is it true to say that A dot A equals or dot or?
Yeah.
Yeah. Is it true? Oh, sorry, to square these and then say this, yeah? Then is it true to say that minus or dot or plus A dot A equals 0? Is it right to do this?
Yes.
Yeah, so you can continue in this way. In other words, you can go backwards through your steps and you must end up with, A or dot or B equals 0, which means A or is perpendicular to or B. So because this is true and every step here is correct, then it must mean that this one was true. This is the idea. It's like the trigonometry proofs. You continue until you get to a statement which is obviously true. Yes. What are we thinking? That's what I thought. Right, now, let's have a look here. You get these on the exam.
Every time.
Let's see which one came. Yeah, so if you look here, 1 to 8 are like the first example I did, whereas 9 to 12, you need to draw something.
Cube.
Yeah.
Circle.
Which one?
The.
Which one? Speak up.
The other question.
Which one? Dude, which one? Other question. There's 12 questions here. What are you looking at?
The 11th question.
Okay. Yes? What's your question? You want me to do it?
Done.
What?
You want him to do it?
So what do you want? In number 11, Tekken, what you're trying to prove is that when you have a parallelogram, yes, that if you take the 4 squares on the 4 sides, that the area of these 4 squares is the same as the area of the diagonal here and the area of the square on the other diagonal.
What's the diagonal?
The diagonal is the line that goes from one corner to the other corner.
So the diagonal is two diagonals.
Yeah, it doesn't matter, just do it for one of them.
Of course one of them.
Yeah.
Or two.
No.
Two could be like this.
True, yeah. If you want to leave number 11 to see it in class, that's fine. I think 9 and 10 should be okay. 9 is good. 9 says, prove that if the diagonals are perpendicular, then the shape must be a square. I think because that one's like the example I did, where because you're talking about perpendicular, it means the dot product is what? 0. And to prove, how would you prove that the shape is a square? That the 4 lengths are the same and that each corner makes 90. Do you know? So actually I think you'd be okay with number 10. Look, try these for a few minutes, okay? Try them for a few minutes.
9 to 11?
No, start with number 1. They're easier at the beginning.
We did number one.
So what are you complaining about? Then jump on to 2.
We did number 2.
Did we?
Yes.
Really?
Yes.
Show me.
When in previous class.
No, we didn't. Well, we did it for particular numbers, but not for like ABC, alpha, beta, gamma. Did we?
You can waste more time to find it rather than doing it.
I think so.
A plus B equals to B plus A. Sure.
Yeah, but where's the proof?
I didn't write it down.
Oh, well, you can write it down now.